Hi, my name is Gokul, and welcome to the talk titled Machine Learning 101. So before we start, just a little bit about me. I'm an Intel innovator, which is the title that you get when you're part of the Intel Software Innovator Program. I'm doing my master's at ETH Zurich, and my work mostly is around generative models for astronomy. If you're interested in that, you can check out the link over there, space.ml. And this summer I interned at Google Research, working on more generative models related stuff. And if you're interested about it, I'll be in the after party, so you can talk over there, or else you can reach out to me on Twitter at GokStudio, or that's my email ID. And we'll be sharing the slides as well, right, after the talk, so you don't have to take notes. So the talk is going to be about the what, when, and why of machine learning. So we're going to an overview of common machine learning algorithms a bit before the neural network craze came in. And then, of course, we're going to talk a little bit about what neural networks are, how do you learn in neural networks, and what's deep learning. And finally, we're going to talk about convolutional neural networks, which are the common architecture that's being used widely nowadays. So the first question is, why machine learning? Like, what's wrong with conventional software engineering? So if you take a look at software engineering, there comes a problem statement. For example, they ask you to create a credit card payment portal. And then you write down the logic with UML diagrams and which object does what, and then you just code it up. But if your task is something like, tell me if there's a cat in the picture, or identify persons in a picture, if you want to do that, then you could do something like templates. You can say, OK, a cat has whiskers, a cat has ears, and then you can try matching that templates with images. But the problem is not all cats are same, and depending upon which angle you take the photo from, the cat face is going to change as well. So if you want to build templates like this, then you have to consider for each case, each species of cat, and you need to create these templates one by one. And that's not going to generalize, because the moment there comes a new photo of a cat, I don't know, from top, your model's not going to work. So the idea is that instead of creating these templates by yourself, why not learn it from the data? Suppose if you have a bunch of images of cats, you could then maybe figure out what a cat looks like from these data sets. Okay? And as we go through the talk, you'll see that the algorithms that we talk about are not something new. These have been around since 1960s, some even in 1800s. So why is the craze right now and not before? It's simply because right now data is abundant. You have websites like Pinterest, Instagram, YouTube. In fact, the entire internet is a data set of text. So you have a lot more data, access to a lot more data that you didn't have before. And you have more compute. Thanks to Moore's law, the number of transistors on a processor increases every 18 months, and you have new hardware as well, things like GPUs, you have FPGAs. You must have heard of Intel's compute stick. Does anybody have heard of that? Okay, one person. Okay, so I have a lot of work to do here. So, and inexpensive storage. Back in 1950s, 5 megabytes of data cost more than $1 million, and it took the entire room to keep it in. But now 1 terabyte costs around 100 euros, and it fits in your pocket. So that's great for us. And you have libraries like scikit-learn, TensorFlow, PyTorch, which make these really easy to use. Earlier, you need to read the papers, you need to understand how it works, you need to implement on your own, then you have to debug it, so on and so forth. But right now, here you could just call a function and get it over with. So how many of you know a proper scientific definition of machine learning, not what you see in newspapers? Anyone? Right. What do you think machine learning is? Okay, so the problem is there's no one definition that everyone agrees, okay, this is, when I mean machine learning, this is what I mean. There's no one definition for that. But this is from Tom Mischel. He's the head of machine learning at Carnegie Mellon University. So it goes like this. A computer program is set to learn from an experience E with respect to some class of tasks or just a task T, and a performance metric P if its performance in task T blah 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 improves. Basically it means that you have a program does a task, and you have a way of saying how good it is doing at the task. So through some experience, if the program's performance improves, then we say it's learning. For example, in the previous slides, the task is basically to detect if there's a cat in the photo. And the experience is to show the program photos of cats and photos without cats, saying, look, this image has cats, this one doesn't. And your performance metric would be basically accuracy on the task, percentage of correctly classified images, for example. So currently, in the mainstream, machine learning can be divided into two parts: supervised learning and unsupervised learning. Supervised learning can further be divided into regression and classification. Unsupervised learning, the most widely used unsupervised learning technique is clustering. There are several more that are available. I'll go through that. And if you check the website, there's also something called reinforcement learning. I will go through this, but these kind of encompass most of the work that's going on in industry right now. So let's go on to supervised learning. So in supervised learning, you have a bunch of attributes. For example, if you want to predict the age or gender of a person, you have attributes like height, weight, maybe color of the skin or length of their hair, so on and so forth. And if the thing that you want to predict is continuous, if it's like floating point numbers or 0.12, something like that, then the set of algorithms are called regression. And if you want to predict something discrete, that means one of five items, or for example, in gender, male, female, or any of the other 48 things that Facebook allows you to keep. So the term supervised comes from the fact that the original labels, right? For example, in an image, you have a label that, yes, this is a cat. It's supervised, kind of like a supervisor. It tells how well your model is performing on the task. So you have the original labels, and that you can use as a ground truth, so to speak, to figure out how good your model is working. So, and supervised learning is really important because almost all the machine learning that's deployed in industry is based on supervised learning. For example, Google Translate, that uses supervised learning. Google Photos, they use supervised learning as well. Common examples like if there's a credit fraud, if a credit card transaction is a fraud or not, these are supervised learning. So if you don't understand any other part of the talk or don't care about the other part, I think you should focus on supervised learning because there's a lot of promise and a lot of money to be made here. Okay, so regression. So in regression, you have a bunch of attributes, let's say x1, x2, so on up to xn, and you want to find out a target y. So for example, let's say you're given for a building, you're given a number of rooms, the building area, things like maybe does it have a front lawn or how many floors the building is, and given these, you want to find out the real estate value. Suppose you want to sell your apartment. You want to figure out how much can I ask for, like what's the going rate. So that's one example of regression. And the model that's commonly used is called linear regression, where you want to fit a line to the data set. The linear comes from here, from the point of fact that there's a line that you want to fit to your data set. In higher dimensions, it's something like a hyperplane. For example, okay, sorry, no, then there's no hyperplane. It's just a line that you want to fit to your data points. So Yeah, this works, and in most cases, if you have a data set, don't even think about it. First thing that you should try out is fit a line to it and see how it works. If it works fine, then you're almost done. If not, for example, if your data set is something like a parabola or a curve, then fitting a line does no longer make sense, right? You want to have terms like x squared or x cubed and so on, right? So if you want terms like x1 square, x1 cube, or so on, or if you want to have like interaction terms where you want to multiply two components together, so if you want to do this, you can reformulate the problem by saying that I'll define a new variable z2 as x1 square, z3 as x1 cube, so on. Okay, you can just add another column called z1 with these values, and you can model your problem now as, okay, earlier it was y equals x1 plus x2 so on xn, then you just add the extra components. Now the interesting thing about this formulation is that it's still linear, right? But you still have the x squared components hidden inside z2. So it's still linear in what's called the feature space. Feature space right now is x1 to xn, then z2, z3. But it's non-linear if you consider just x1 to xn, right? Am I making sense or? Wait.
Can I have a question?
Sure.
What mathematical operations make sense in creating features?
So to repeat this question, you want to?
What mathematical operations make sense when creating features?
Okay, so the operations that you want to apply depends on the datasets and the error that you have. For example, if in this dataset you had points which are going like this, right? Then it makes sense for you to see, okay, maybe a line doesn't fit well. So I want to look at something like a parabola. So you'll say, okay, x squared. And if it goes something like this, which is a cubic part, then you say x cubed. So generally you want to keep a monotonic function or something that doesn't give you infinity. For example, if you have negative values, you should not use log. For example, it's better to use exponentials for those. So it depends really on the kinds of errors that you get with your line. If you take a line and then you see, okay, how much deviations am I getting from the actual data point to the line, depending upon how the deviations are, then you can plug in things like x squared, x cubed, so on. So to answer your question, keep it as simple as possible. Polynomials work great most of the time, and the degree of the polynomial depends upon how the trends in the error. Okay. Any other questions so far? Okay. So the next is classification. In this case, it's still supervised learning, and the target right now is discrete. That means you want to find a label from a discrete set of labels. For example, male, female, the 48 other things, or things like cat, not cat. That's classification. Another common example is spam versus not spam. Your email filters, cat versus dogs. Digits, there are only finitely many digits, right? 0 to 9, characters A to Z. So those two can be considered as classification. And recently, you might have heard of things like ImageNet, the dataset, MS-COCO, CIFAR10 or CIFAR100. These are image datasets that are used frequently in deep learning, and basically these are just images with a fixed label and other attributes. Okay, so the most common algorithm that you use in classification is what's called as a decision tree. To understand a decision tree, you can think about in programming when you have an if-else block. So you can read it off as an if-else block actually. This is basically this is a decision tree that you might use if you want to go for a hike. If the outlook is sunny, then if the humidity is high, then I'm not going to a hike. Else, if the humidity is normal, then I'm going to a hike. If the outlook is overcast, yes, then I'm going to hike. So decision trees have been around since I think 1970s, and they work really well for things like credit card, fraud detection, things like whether given a person who comes and applies for a loan, do we want to give him a loan or not, things like that. And these have been used widely in the financial sector, and they work really well. And the best part about this is that these models are interpretable. So if the model says no, do not give him a loan, then you can actually ask, okay, why should I not give a loan? Then it will say, oh look, usually people with so much income and or who have this kind of credit history have a history of not repaying back their loans, so you should not give the loan. So the advantage of using decision trees is that it gives you interpretable predictions. Okay, and the way you learn decision trees, there's a lot of theory behind it, so I won't go into that, but if you're interested, you can ask me after the talk or during the after party, as you like. So classification, there are more examples like support vector machines, which are again simple a line which divides the data set into two classes, plus and minus. So it's a bit more complicated than that, but in this logistic regression, this gives an idea of what is the probability of a data point belonging to a class. So this gives you a probabilistic interpretation, which helps you give an idea of certainty. For example, if the output of logistic regression is 0.9, you can say that I'm 90% confident that this data point belongs to a class. A naive Bayes classifier, it's a simple application of the Bayes rule. Okay, and k-nearest classification, in this one, how they assign the labels is the label of a data point is the majority of k nearest neighbors to that data point. So for example, if you have in 2D space, you have a point and it's surrounded by points belonging to a blue class, for example, then you'll say, okay, that point also belongs to the class blue. It makes logical sense. So next we go on to unsupervised learning. In unsupervised learning, simply said, there are no labels, so therefore there's no guidance, there's no supervision. So usually the problem sets are like your boss comes to you and says, hey, here's a data set, get me something interesting, right? As a human, it's really annoying, but you still come up with something. But as a machine, it's really difficult for it to understand, okay, what is interesting, right? So like I said, it's really hard to define, and it's more of, if you can't have an objective, right? If there is no value that you want to maximize or minimize, then comes the question of, okay, how are you going to optimize for the problem? Like if you remember the definition, you had a performance metric for the task. In unsupervised learning, it's usually the case that you don't have a performance metric. So how can you say that your model is learning or not? So that's a big confusion. But the current models that are commonly used in this case are clustering algorithms, and even otherwise, even right now in the deep learning field, it's a really hot area of research because people have no clue how to do unsupervised learning. And it's really important that we understand and do unsupervised learning because most of the data out there, almost 80% of the data, is unlabeled. It's just as images, for example. You don't know the labels for that, and you really like to use that data. Okay. So I'll move on to clustering. The clustering, you have a data set that consists, each data point is an n-dimensional vector, so like n numbers. Okay, and in clustering, what you do is you clump similar data points together into the same cluster. Like you say, okay, these points which are close by belong to the same cluster. Okay, and the notion of similar varies from your use case to use case. For example, if you have just a vector of numbers, you can just compute something like L2 distance, or if you have two document vectors, like numbers that correspond to two documents, you can calculate what's called cosine similarity, which gives you an idea of how similar two documents are, or how dissimilar two documents are. You could use L1, which is like, instead of using an under root, you just take modulo of each of the components. Or another thing that people use is reachability. In that, what you say is, you take a point, you take a radius r, and you say all the points that belong that are inside a radius r are similar. Okay, and you can have any other definition of similarity you want depending upon your use case. So, and depending upon the algorithm that you use, there are different clustering methods called k-means, which is basically like the mean. The center of a cluster is the mean of all the points that belong to a cluster. K-medoids is similar. Instead of taking a mean, you take a median. Gaussian mixture models model the entire data set as saying, okay, I have n different Gaussian distributions that give rise to the data set, and I want to figure out the mean and variance of each of the variance or covariance of each of the distributions. And dbScan optics and spectral clustering are built on k-means and k-medoids. They solve some of the drawbacks of k-means, and dbScan works on the idea of reachability. Like, from a given point, you look for the any points that are the distance r, and you put them in the same cluster. Okay, and like I said, there are other forms of unsupervised learning models other than clustering. Another one is regeneration. In this, what you have is it's easy to understand it this way. You have a model. Okay, you feed in an image, and one part of the model compresses into a small vector. For example, if you feed in an image of dimension 28 cross 28, that comes around to 7 to 84 size vector, and it compresses down into a 100-dimensional vector. Okay, and another part of the model takes this small 100-dimensional vector and tries to recreate the image. Okay, so the model can do that if and only if it has learned something interesting about the data set. If not, it cannot just recreate an input from a small vector. Okay, and there are other things called generative models. Two of the popular architectures that are used are GANs, which are generative adversarial networks, VAEs, or variational autoencoders. Both of these are both of these use neural networks, so I won't go into them, but my work has been around these models. Okay, and another thing that you might not have realized is a form of unsupervised learning is dimensionality reduction. Things like PCA, SVD, and t-SNE. You usually use them as a pre-processing technique. If you have, say, 1,000-dimensional data set and you want to reduce it to 100 dimensions, usually what you do is PCA or SVD. If you think about it, these models can do the dimensionality reduction only because they understand there's something interesting in the data set, and they can say, okay, these parts are interesting, these parts are not interesting, so I'm going to throw them away. So if dimensionality reduction is in another way of unsupervised learning. So I'll share the slides so you don't have to worry about it. So this is just basically a cheat sheet of if you're using scikit-learn for your machine learning models, which one to use. So you start from the start, obviously, and if you have less than 50 samples, you need to get more data. If you have more than 50 samples, then you have a question of whether are you in classification or regression. And then there are a bunch of models that you can try out: SGD classifier, linear SVC, k-neighbors classification, and so on. So this kind of gives an overview of the supervised and unsupervised learning algorithms that are supported in scikit-learn. And most other frameworks, like for example Google machine learning or Microsoft Azure machine learning frameworks, they support most of these algorithms, so you can plug them in and see which one works. So I said just supervised and unsupervised learning, right? So there are other kinds of learning as well. One is semi-supervised learning, wherein if you have a million images, instead of going and labeling each and every one of them, you just say, okay, I'm just going to label 100 or 1,000 of these images, and the model is supposed to figure out the labels for everything else. So it's supervised, but the rest of the data sets has no label. So that's why the name semi-supervised. There's another type of set of algorithms called active learning. In this case, there are no labels, but how this goes is you give the entire data set to the algorithm, and then it says, okay, I need the label for this data point. So you go and compute the label for that, and it goes. It's an interactive kind of an approach, so to speak. Okay. And then there's reinforcement learning. There's an entire talk about it coming up. And then there's something called as transfer learning. In transfer learning, the idea is that the things that you learn for similar tasks, for example, if you have a neural network that you train for image classification, right, cat, dog, or anything else, you can use what you've learned for another similar task. For example, object detection. An object detection is basically you have a photo, and you want to detect okay, this box contains a cat. So it makes sense for us to use the weights from the image classification task for the object detection task. Okay, so that's what transfer learning is about. Okay, and now this was all about classical machine learning algorithms. We need to go deeper. Okay, and address the AI hype. So the second line is basically what all of deep learning is. You have a bunch of matrices, then you multiply them one after another, and people go crazy because of that. I don't know why. Okay, so just to give if you already used neural networks before, or if you're a beginner, neural networks are loosely based on the human brain, and they don't interpret anything from that. It's just a statement. Yeah, it's loosely based. Okay, and in technical terms, it's a sequence of matrix multiplications followed by an element-wise nonlinearity. I'll come to what these are, but a neural network is basically just that. You have a bunch of matrices. You take an input. You do a matrix multiplication. You do an element-wise nonlinearity, so on and so forth until you get the output. Okay, there are different types of neural network architectures or building blocks. The two most common one are CNNs, convolutional neural networks, which are used for image and video, and more recently for text as well. And recurrent neural networks, where you want to remember something. Okay, and these are used for text, which is a sequence of characters, or other sequences like weather forecasting or anything like that. Okay, to understand how you learn in a neural network, you need to understand the computational graph model of neural networks. So let's say E is your output, okay, and E depends on C and D, and you define C as A plus B. So C depends on A and B, and D is defined as B plus 1. So D depends on B. Okay, so learning happens it's a game of blame. Seriously, if the output is wrong, right, now you need to blame someone. That's literally what's happening in gradients and backpropagation. So if your E is wrong, so who's responsible for E? C and D. So you need to pass on the blame to C and D. And since C is wrong, right, who's responsible for that? A and B. So you need to pass it back. So that's kind of the intuition behind backpropagation. You have an output, you know it depends on C and D. So you compute the gradients or its partial derivatives with respect to C and with respect to D. And you tell them, look, my output is wrong. It's wrong because you gave me the wrong inputs, so you need to change. And this is kind of the gradient gives an idea of how much you need to change. And there's another hyperparameter called learning rate. You just multiply your gradients with the learning rate and you update weights. That's how backpropagation works. You start from E, then you update C and D, and then you update A and B in a very overview sense. But there are a lot of optimizations and numerical things that I won't go into. Okay. And finally, before I start, any questions? Okay, cool. So the final part of the talk is about convolutional neural nets, or CNNs. The main components of a convolutional neural net are the convolutions themselves, and there's another layer called pooling, and then finally fully connected layers. So convolution, to understand what's happening in a very simplistic way, you have an input matrix, right? And you have a filter, which is just another smaller matrix, and you just slide it across the input, okay? And every time the input and the filter overlap, you just compute the dot product. You take multiply these two elements, sum it up, okay? And that's how a convolution works. For higher dimensions as well, you can imagine instead of just matrix, you have more matrices stacked up each on top of each other. So that's how convolutions work. And there's after convolution, right? After you do this multiplication and you get a number here, you do something called as an activation. An activation is basically an element-wise nonlinearity. Element-wise meaning that you apply this function to each one of the elements independently, okay? And you call it nonlinear because the functions that I'll be showing, they are not linear in a way. They use, for example, exponents in a sigmoid, or hyperbolic tangent, which is a difference by sum of exponents. A ReLU, which is a simple max of 0 or x. So this is like a flat line, and then from in the negative x part, and then a straight line in the positive x part. And then you have another thing called leaky ReLU, which is a max of 0.2, or it could be any other number less than 1. So it's a straight line in the positive x direction, and a less, you can say it's a less steep line in the negative x direction. And pooling is basically used because you want to reduce the dimensions. In the operations that we've seen so far, there is no dimensional reduction. If your input is 5 cross 5, you will still get some 5 cross 5 or something smaller. Pooling is used generally in a sense of, I want a summary of the dispatch, for example. You want to reduce the dimensions, so you take a subset of the dimensions and you get a summary. So the two commonly used pooling methods are average pooling and max pooling. Average is just, it's a 2 cross 2 grid, right? So you take an average of these numbers, and in max pooling you just take the max of the 4 numbers here. So that's simply what pooling is. And the final thing is something called fully connected layers, or dense layer, depending upon which framework you use. And it's again a simple matrix multiplication followed by an activation. Okay, you can write it as a sigma times W transpose X plus B, and sigma is an element-wise nonlinearity, like we have I've shown in the previous slides. And the B is a bias, so that you can learn things which do not, you can learn things that are not centered at the origin. Okay. It's like this is the final slide. Sorry. So this is kind of what I've shown so far is the standard CNNs that people use, and it's a classic. So the current questions that people are asking and answering are, how deep can we go? You've seen AlexNet or things like that, which are 15, 16 layers deep. How deep can we go? So the answer is very deep, and the paper is called ResNet, or residual networks, and they show that you can have neural networks which are more than 1,000 layers, 100 layers here, and they've shown that you could do it for even 1,000 layers, and it's from Microsoft. So it's a really good paper. You should check it out. And then the second question is, can I build these neural networks with less memory? And the reason for this is that these neural networks are usually used for video or image related tasks. Wouldn't it be cool if your phone, if your camera app could support these things? You could point it out, you could point your phone at something and say, hey, it's a flower or whatever. So if you want to put it into things like phones and embedded systems, they need to use really low memory. One cool example is called SqueezeNet, and they give really good performance, and the size of their model is less than a megabyte, to be precise, like 512 kbs. And their performance is as good as AlexNet, which was the 2012 winner of ImageNet Challenge. And then the next question that people want to ask, which is also linked to the less memory problem, is, do we need all the precision? The weights that you saw so far are floating point numbers, which are like 32 bits. And the answer is no. And the actual thing is, if you just have plus and minus 1 in your weights, it's a binary number, right? Instead of 1 and 0, you have plus and minus 1. If you have plus and minus 1, you can still have really good performance compared to AlexNet. And you need to change how the convolutions work, but it's pretty simple. And the paper is called XNORNet, where XNOR because they replaced the convolution operations with XNORs. Okay. And the final is, how do I do things like transfer learning? Use trained weights for different tasks. Okay. Weights trained on image classification to object detection. And the common architectures that people use is VGG16, which is, I think, 16 layers deep, of course, and Inception V3, which is from Google. And the final thing that people ask is, can we replace the fully connected layers with convolutions? Because the fully connected layer is a matrix multiplication, right? So matrix multiplication is order n cube, or order n 2.7, but whatever. So it's order n cube, and so compared to convolutions, it's extremely compute intensive. So people want to figure out if I can replace the fully connected layers with a convolution. It turns out, again, the answer is yes. And you can Google the title, fully connected, fully convolutional networks, and they performed really well. So, yep. Any questions?
Time for questions. We have a question in the back.
Yay!
You mentioned something about the usage of CNNs to text. Could you please expand if you have a second?
Sure. In text, the first thing that people do is, you've heard of word embeddings, right? So to use CNNs for text, the first task that they do is convert the words into word embeddings, right? So now you have a sequence of vectors, And what they do is they slide the convolutions over over the entire vector. And the pooling that they do is something called global max pool, which is basically they take the max of each dimension. Okay, if you have 5 filters and you slide it through the entire sequence of word embeddings, and then you take the max, so you will have just 5 numbers. So in that way, from a non-fixed dimensions, you get it down to a fixed number of dimensions, and then the normal convolution thing goes on. So the basic idea is from text you go down to word embeddings, and then you slide a convolutional filter throughout it, and you take the global max or global average for each of the dimension. So you have a finite dimensional vector. Does that make sense? Or cool.
Okay, more questions? Last year for vacations we had a guy from Samsung talking about squeezing the networks into this model. You put new things, and that was science fiction. Okay, more questions? So if not, you can find Gokula during our after party. So big applause. Thank you.
Thanks.